So now we will talk about azimuthal quantum number. Azimuthal quantum number. It is also known as angular momentum quantum number, and it is also known as subsidiary quantum number. Subsidiary quantum number. So there are actually three names of azimuthal quantum number. First of all, it is angular momentum quantum number, subsidiary quantum number. So we will also talk the reason that why the azimuthal quantum number is known as angular momentum quantum number. So what actually the azimuthal quantum number shows you? It shows you the shape of orbital. It represents you the shape of orbital. So now we have talked about shells, right, which is K element. Now we will talk about subshells. And these subshells, how we represent them? We will represent them with L, and they start with whole numbers. Like in the shells, they were starting from natural numbers, which is 1, right? But here the L, which is subshell, actually it will start from whole number. So the first subshell is 0, which is S, 1, which is P, 2, which is D, 3, which is F, and there is one more G, H, but an element with G is not discovered yet. So what does S shows? The shape of orbital, which is spherical. P, which is dumbbell. Let me write here, it is spherical. So the shape will be like this. It is known as dumbbell. D is double dumbbell. It is like this. This is known as D, and F is quite complicated. It is having 8 folds. So what does the azimuthal quantum number shows? Azimuthal quantum number shows you the shape of the orbitals. Like now these orbitals, you can say these are the subshells, right? Shell were KLMN, and L shows the subshell, which are S, P, D, F, right? So now let's look. In shell number, this is N, this is L. If you're having shell number 1, how many L will be here? So there is a formula for that, which is there's a formula for finding that in this shell how many subshells will come. So it's now shell number 1. So how many subshells will come? 0, which is S, 1S, right? In shell number 2, 0 and 1, which is 2S and 2P. In shell number 3, 0, 1 and 2. So here 3S, 3P and 3D. Like in shell number 3, how many subshells will come? 3S, 3P, 3D. It is shell number 4, 1, 2, 3. So here 4S, 4P, 4D and 4F will come. So what does the azimuthal quantum number shows? It shows you the shape of orbitals. S stands for spherical, P for dumbbell, D for double dumbbell, F for complicated, which is having 8 folds. So you can see that in shell number 1 only one suborbital. Like you can there is a rule like number of shell is equal to number of subshell, right? If you want to find like how many subshell will come in shell number 3, so there will 3 subshell will come. If you can see here over here, like it is shell number 3 and there are 3 subshells for it. So you can easily find by this technique like how many subshells will come in a shell. So now I hope that this concept is clear to you. Now let's talk about why azimuthal quantum number is known as angular momentum quantum number. So there is a formula for that, which is orbital quantum number, right? There is a formula which is h upon 2 pi radical L upon L plus 1. Like this is the formula for finding orbital quantum number, where L is subshell, right? SPDF. Okay. So for example, I'm saying that find orbital angular momentum of an electron in 3p shell. Like there is an electron, right? And you have to find the angular momentum of that electron in 3p shell. So now if by using this formula, h upon 2 pi radical L, how we will know that how many L? So I have told this number shows you the shell. So number of shell is equal to number of subshell. So L is equal to 3 like L plus 1, right? Now 3 plus 1 is equals to 4. 4 multiplied by 3 is equal to 12. Okay, actually leave this. Okay, actually what it is, like you have to tell the orbital angular momentum of an electron in 3p shell. Like if the electron is in 3p shell, in this shell, in 3p or p subshell and 3 shell, so what will be its angular momentum? So we know 3 is n is equals to 3, p is equals to, like s is 0, so p is equal to 1. So here the formula will be h upon 2 pi radical L, which is 1, L plus 1 plus 1. So 1 plus 1 is equal to 2, and 2 multiplied by 1 is 2. So h upon 2 pi radical 2 will be the angular orbital angular momentum of an electron which is in 3p shell. Or you can find that, for example, we can find the orbital angular momentum of an electron which is traveling in 4s shell. So here n is equals to 4 but L is equals to 0, right? So here h upon 2 pi radical 0 plus 1. So 0 plus 1 is 1. 1 multiplied by 0 is 0. So the whole value will be equal to 0. So the orbital angular momentum of an electron which in 4s shell is equal to 0. So I hope the concept of azimuthal quantum number and why we call azimuthal quantum number as angular momentum quantum number, and it is also known as subsidiary quantum number.